Good day, and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is variable resistors. Our objective today is to take a close look at a three-terminal variable resistor known as a potentiometer. Even with a dizzying array of standard resistor values available, you're sometimes left scrambling for a specific resistor size. Recall our earlier discussion during the resistor color code lecture available at the Big Bad Tech channel, where I sent you on a wild goose chase for a 140 ohm resistor. This resistor isn't commonly available via the standard size set. We had to resort to some level of trickery to accomplish the desired task. Given the tolerance rating of commonly available resistors, you might be able to paw through a roll of 5% tolerance 130 ohms or 150 ohms, the next lowest and highest standard resistors available, to find an unusually high 130 at 136.5 ohms or an unusually low 150 at 142.5 ohms. I know there isn't a true overlap between these two steps of plus or minus 5% resistors, but come on, really, either of these two is going to do the job of a 140 ohm resistor just fine. Additionally, understanding basic series and parallel manipulations, you realized we could in effect create a 140 ohm resistor by placing a 120 ohm in series with a 20 ohm, or by using two parallel sets of a 270 in series with a 10. It should be evident that these are not the only two combinations of standard size resistors that would yield in effect a 140 ohm resistor. You could take 7 20 ohms in series and make it a 140, 14 10 ohms in series and make it a 140, or 140 1 ohm resistors in series and make that a 140 ohm resistor, all with an increasing level of annoyance and busy work. It would be far more desirable to use a single resistor in which you could dial it into the exact value you require. This device is a potentiometer, sometimes known as a rheostat depending upon application. Informally, they're known as pots, trimmers, or a combination of both, trim pots. A potentiometer is a three-terminal device, and the two outside terminals, A and C, represent the beginning and end of a conductive path with a constant resistance. They're often blue, gray, brown, or black plastic boxes with an adjustable screw, or a plastic wheel, or perhaps circular devices with a knob and leads. The A2 resistance is the nameplate value of the potentiometer and is often printed in small illegible print on the outside case. A 1K potentiometer always has 1 kilo ohm of resistance from A to C or from C to A, regardless of the position of the adjustable screw or knob. A 2K potentiometer always has 2 kilo ohms of resistance from A to C or from C to A, regardless of the position of the adjustable screw or knob. Get it? The schematic symbol for a potentiometer reveals the purpose of the middle lead B. It is a midway station on our journey from A to C. What's super handy about this midway station is that the physical position of terminal B is adjustable via the screw, the knob, or the wheel. This movable B contact is sometimes called the wiper arm because it slides up and down the resistor from A to C. In effect, we are varying the length of the conductive path from A to B, or just as valid, from B to C. If we remember correctly from our resistance lecture, length is one of the three main properties that influence resistance, in addition to resistivity and cross-sectional area. If I increase the length, I increase the resistance. However, since the resistor from A to C is of fixed length and fixed resistance, every time I increase the length of the A to B path, I am decreasing the length of the B to C path. Can you see where this is leading? The resistance of the path from A to B plus the resistance from B to C is always equal to the resistance from A to C. This can be expressed mathematically as RAB plus RBC equals RAC. Again, regardless of the position of the knob, the resistance from A to C is fixed, and it will represent the maximum value of our potentiometer. If it helps you to understand three-terminal potentiometers, you can visualize the internal structure of a potentiometer as a pair of series resistors, RAB and RBC. If you increase RAB by 1 ohm, you decrease RBC by 1 ohm, and vice versa. There's a little dude in there. Seriously, there is. And he's got a tiny dump truck that shuttles a fixed quantity of ohms back and forth across the center terminal. Sometimes in schematics or circuit simulation programs, there's a positional indicator in units of percent. Think about what this means. If a 1 kilo ohm potentiometer is set at 50%, the B terminal is halfway between terminals A and C. Therefore, the resistance from A to B is 50% of 1 kilo ohm, or 500 ohm. What's the resistance from B to C? If RAC equals RAB plus RBC, RBC is equal to RAC minus RAB, or the other 50%, or 500 ohms. If we adjust this 1K potentiometer B terminal to a 60% position, where 60% of A to C is experienced on the A to B side, RAB would be 60% of 1 kilo ohm, or 600 ohms. Again, it would stand to conjecture that RBC is the remainder of the nameplate value, or 1K minus 600, or 400 ohms. The percentage scale is always referenced from A to C, and not the other way. Therefore, RAB would be equivalent to the position in percent times RAC. If you accidentally hooked up the potentiometer from B to C at 60%, you'd get 400 ohms, not 600 ohms. Ask me why I'm making a big deal about accidentally hooking things up backwards, because it happens more often than one might expect. Stay organized. I'll return to lab practices in a bit. Consider the following scenarios with 4 different potentiometers with the following values. Pause the lecture and see if you can figure out the unknown values. For our first example, where RAB is exhibiting a resistance of 100 ohms and our total resistance RAC is 2 kilo ohms, we could make use of the fact that RAC equals RAB plus RBC. Substituting in the known values and solving for RBC, we find that RBC is 1,900 ohms, or 1.9 kilo ohms. If we wanted to know the position and percentage to obtain 100 ohms from a 2 kilo ohm potentiometer, we'd use the relationship RAB equals our position times our total resistance RAC. Given we know RAB and RAC, we can solve for position as 0.05, and if we wanted to express that as percentage, it'd be 5%. The remaining 95% is on the other side of the potentiometer, or the 1.9 kilo ohms exhibited by RBC. For our second example, with a 1 kilo ohm potentiometer exhibiting 780 ohms between the B and C terminals, we'd realize that RAB would be 1K minus 780, or 220 ohms. If we wanted to determine the position indicator and percentage, 220 divided by 1K is 0.22, or 22%. Our third example requires a little thought. A potentiometer exhibiting 400 ohms from A to B at a position of 20% means the other 80% is on the other side. 80% is 4 times as much as 20%, so 4 times 400 is 1,600 ohms. If RAB was 400 ohms and RBC was 1,600 ohms, our AC should be equal to 2 kilo ohms. Additionally, you could solve for the unknown total resistance using the position indicator and the known resistance RAB, where 400 divided by 0.2 is 2 kilo ohm. Now, knowing that we have a 2 kilo ohm resistance, RBC would be similarly solved for at 1,600 ohms. Our last one is terribly easy or terribly hard depending upon your visualization skills. In the case of 100% position, the B terminal is jammed all the way to the C terminal. All 3 kilo ohms are on the RAB side. What's left over on the RBC side? RBC would be 0% or 0 ohms. In this case, 3 kilo ohms plus 0 equals 3 kilo ohms. The point of this repetition was just to show you can't get more resistance out of a potentiometer than what's in there. Additionally, it goes to show you that you can create 0 ohm paths inside circuits if you take a potentiometer and adjust it all the way to one side. Remember the warning I gave you about inadvertent 0 ohm paths inside circuits? They're generally not considered a recommended practice. An accidental short directly across the terminals of a voltage source is a bad idea under full sail. Don't do it. Think about it before you act. Don't just randomly flail in lab and push buttons, pull wires, turn screws, and hope it works out okay. Imagine how well lab will go if you know what you're doing. As further illustration of this concept, consider the following circuit incorporating a potentiometer. What is the resistance seen by the source for this 1 kilo ohm potentiometer at 80%? Pause the lecture and see if you can figure this out. If you got anything less than 1 kilo ohm, have you been paying attention? Look at the circuit. How is the potentiometer hooked up? It's hooked up between terminals A and C, and regardless of the position of the adjustable knob, the resistance between the A and C terminals is 1 kilo ohm. Basically, you're using this 3-terminal adjustable potentiometer as a 2-terminal fixed 1 kilo ohm resistor. You can do that if you want to, but it's not really the intended purpose of an expensive adjustable device. Just grab a cheap fixed 1 kilo ohm resistor if you want a constant 1 kilo ohm resistance in your circuit. Again, I could cycle terminal B's position from 0 to 100%, and the resistance from A to C would never change. Now consider the following circuit where the 1 kilo ohm potentiometer at 80% is hooked from A to B in our circuit. What's the total resistance seen by this source? The answer is 80% of 1 kilo ohm, or 800 ohms. What if you were to accidentally install this potentiometer upside down though? In this case, you'd be using the B2C portion, or RBC, would be the remaining 200 ohms. The point is, what's the A terminal, what's the B terminal, and what's the C terminal? Figure it out. This is where lab practices, organization, and discipline come into play. Different manufacturers label different terminals differently, and sometimes they're in different places. I often refer to the B terminal as the center terminal. Is B really in the center? It'd be nice, but it might not be. Figure it out. Let's say you get a 3-terminal potentiometer with absolutely no external markings on it at all. How would you figure out which terminal is which, and in which direction turning the adjustable screw increases resistance for the RAB portion of our potentiometer? Here's what I'd do. I'd use an ohm meter and measure its resistance at specific combinations of terminals. I know we haven't gone into specifics about ohm meters yet, but for now, just pretend an ohm meter is a 2-terminal device that will tell you the resistance between 2 terminals in units of ohms. The potentiometer must be removed from the circuit and must not be powered up for reasons I'll explain later. Now just randomly grab 2 terminals and measure the resistance. When I say randomly, I mean randomly, as in your choice. I don't care. Just grab any 2 terminals. Read the resistance value. Now take a tiny screwdriver and turn the adjustable screw, spin the wheel, or fiddle with the knob. If the resistance reading stays the same, you're reading the resistance of the whole potentiometer, or RAC. The terminal you are not hooked to is B. Here's where it gets crazy. Just call one terminal A and the other C. It doesn't matter if you're matching the manufacturer's pinout diagrams or not. You can flip-flop these two if you want to. Now keep one lead on the one you chose to call A and move the other lead to B. You can now read the resistance of your version of RAB. Now spin the screw again. If resistance increases, you are increasing your version of RAB and decreasing your version of RBC. If resistance decreases, you're decreasing your version of RAB and increasing your version of RBC. Now here's where discipline comes into play. Remember which terminals are which, and remember which direction increased or decreased your chosen version of RAB. Mark one or mark all 3 terminals. Make sure your lab partner knows which one is which and in which direction to turn the adjustable screw. Install the potentiometer in the manner in which it was intended to be installed. A lot of my students take a piece of paper and simply poke the components into it and write the expected and observed values below them and any notes that might need to be accompanying them. An equal number of students just put components in random piles that are easily knocked onto the floor and overlooked. You can guess which student groups have an easier time completing the desired task, and which students just snap at each other and learn nothing. Consider this first scenario in which the potentiometer is hooked A to B and at 80%. The resistance seen by this source is again 80% of 1 kilo ohm or 800 ohm. Now, while the circuit was in operation and current was flowing from our voltage source through our potentiometer, what would happen if I decreased the B terminal position to 70%? Obviously, I would have decreased the resistance to 70% of 1 kilo ohm, or 700 ohms. In this case, resistance or opposition went down, and given our voltage source stayed constant, current should have gone up. Again, what if I adjusted this potentiometer to 50%? Our resistance would be 50% of 1 kilo ohm, or 500 ohms, and our resistance or opposition to current has gone down, and our current should again increase. Now adjust the potentiometer down to 10%. Again, resistance or opposition has gone down, and current continues to climb. Finally, let's be dangerous and jam the B terminal all the way to one side, or 0%. And you guessed it, you're spending the rest of the day getting your lab instructor's boot surgically removed from your backside. Don't do this. Don't short circuit voltage sources. The path must have resistance or opposition for current to be controlled. A path with 0 ohms of resistance is a short circuit and is to generally be avoided. Consider the following circuits in which a potentiometer is employed. Pause the lecture and see if you can determine the total resistance seen by the source for each case. Again, before you even involve numbers, what is the relationship exhibited between the resistors in these circuits? Our first example at the top is a series or an inline relationship, where an 820 ohm resistor is in series with a 1 kilo ohm potentiometer, where 65% of the resistance, or 0.65 times 1K, or 650 ohms, is exhibited between the A and B terminals. In this case, our total resistance is 820 plus 650, or 1,470 ohms of total resistance. Now, consider this series relationship in which the potentiometer is then adjusted from this first position. If one was to decrease the potentiometer to 50%, RAB would be 0.5 times 1K, or 500 ohms, and our total resistance would be 820 plus 500, or 1,320 ohms. Our total resistance seen by the source went down by adjusting one of the resistors in our series combination downwards. Let's say, though, after a healthy breakfast of a couple energy drinks and cigarettes, your lab partner gets a little enthusiastic with a screwdriver and accidentally spins our adjustment screw all the way down to 0%. I know I just lectured you on unintentional short circuits, but will this enthusiastic over-adjustment short-circuit the voltage source in a series configuration of 2 elements? No, there's another element in this single path, the 820 ohm resistor. With a potentiometer at 0 ohms, the total resistance is 820 plus 0, or 820 ohms. Yes, it's much less than our first configuration, but the 820 ohm resistor is still there. In this case, the 820 ohm resistor is the sole current controlling device in our circuit when you've effectively removed the potentiometer's resistance from consideration. For our second circuit, this is a parallel combination of a 3.3 kilo ohm resistor and a 5 kilo ohm potentiometer, in which 20% of 5 kilo ohms, or 1 kilo ohm, is exhibited between the B and A terminals. In this case, it can be simplified as a single imaginary resistor equivalent to a 3.3K in parallel with a 1K, where the simplified resistance is approximately 767.4 ohms. Again, consider this parallel configuration in which the potentiometer's resistance value is adjusted while in this relationship. If the potentiometer was perhaps increased, what would you expect the total resistance seen by the source to do? Again, how should parallel relationships behave? The total parallel combination should always be less than the smallest resistor. In this case, our potentiometer at 20%, or 1 kilo ohm, was the smallest resistor. The total resistance seen by the source when the potentiometer is increased should go up, but it should never be greater than the smallest resistor in the combination. Let's see if this is the case. Let's crank it up to 40%. 40% of 5K is 2K, where a 3.3K in parallel with a 2K is approximately equal to 1,245.3 ohms. There you go. It is less than our smallest resistor, in this case a 2K, but the total resistance seen by the source went up ever so slightly because we increased the resistance of one of the parallel paths while keeping the other constant. What about the opposite case? What if we decrease the resistance value of the potentiometer in our parallel combination? Let's say your twitchy lab partner is again on the business end of a screwdriver, and the potentiometer was dialed from 40% down to 1% of 5K, or 50 ohms. In this case, the smallest resistor in our parallel relationship is now 50 ohms, and the parallel combination of a 50 ohm and our fixed 3.3 kilo ohm resistor should be less than the smallest resistor, in this case approximately 49.3 ohms. What if you didn't stop your lab partner at a time, and they dialed it all the way down to 0%, or 0 ohms, where a 3.3 kilo ohm in parallel with a 0 ohm resistor is 0 ohms, or a short circuit directly across the terminals of our voltage source and to be judiciously avoided at all cost. Can you now see the benefits of having one of those quiet and reserved lab partners that just sits there like a stuffed animal and touches nothing during the course of your studies? In these two scenarios, series and parallel, I illustrated the effects of short-circuiting a single element. In the case of a series circuit, if one element is short-circuited, that single element is effectively removed from the circuit, and the remaining elements have to pick up the slack. Kind of like you and your slacker lab partner's relationship. In the case of a parallel circuit, a short circuit shorts out all elements within a parallel combination, and could potentially have disastrous consequences if that's the only combination opposing current. This is a case where an especially problematic lab partner just blows up the whole lab. A recommended practice is to make sure you know where that tiny screwdriver is at all times. Sticking with this short circuit theme I seem to have developed, consider the following tiny modification to a 3-terminal potentiometer. What if I was to tie terminal B to terminal C using a 0 ohm wire, and I employed the modified potentiometer in the following circuit, A to C inside a path? One might rush to judgment that the full resistance from A to C will be seen by the source. But this is not the case because of the additional 0 ohm path. Stepping back to an earlier model of the potentiometer, recall I introduced it as a series combination of two resistors RAB and RBC. In effect, a 0 ohm path from B to C is basically a 0 ohm resistor in parallel with RBC. What is the parallel combination of anything in 0? The answer is 0. In this case, quite like our earlier short circuit scenarios, RBC would be removed from consideration and the only remaining resistance is RAB. In effect, by tying B and C together with a 0 ohm wire, you're creating an adjustable quasi 2-terminal device. This is a method often employed by a rheostat, simply another word for potentiometer. A rheostat is an adjustable resistor used to control current. This may seem like the exact same purpose of a potentiometer, but full consideration of the fine points for the differing applications is probably just going to confuse you right now. So we're just going to leave that for a later discussion. Just use the term potentiometer and everybody's going to know what you're talking about. Even component suppliers list them in catalogs as potentiometers. If you see a schematic symbol for a 2-terminal resistor with an arrow inside it, kind of like our earlier schematic symbols for the thermistor and the photoconductive cell, if you'll recall, I introduced these two types of 2-terminal variable resistors in the temperature coefficient lecture available at the Big Bad Tech channel. By all means, check this lecture out if you haven't done so already. The astute among you might say, why can't you just use the two terminals A and B or B and C to create an adjustable resistor like we did earlier? Yeah, you can do that too. It makes way more sense. I am in total agreement. If we did that though, we wouldn't have been able to talk about short circuits. Impress you with another synonym for a potentiometer, and it would have been way too easy to understand. Fully half the job of industrial maintenance technicians is to make their jobs seem so outlandishly steeped in black magic they're impossible to do without. Thing is, it's not magic. It's just series and parallel relationships of resistors used to accomplish a specific task. Before we close up shop on potentiometers, let's take a quick look at something known as a voltage divider, and we'll examine unloaded and loaded voltage dividers. This is a preview of series parallel analysis, and trust me, we will revisit this in later lectures, so do not think this is the only time you'll ever see this. Right now, I just want to keep our analysis simple and inside the realm of what we already know, namely series and series parallel configurations of resistors. Consider the following circuit, consisting of a voltage source connected to a potentiometer A and C terminals. What's the big deal, you might ask? Obviously, the source is seeing the full resistance of this potentiometer, in this case, 1K. Yes, this is true and represents the undisturbed ideal state of an unloaded voltage divider. Pause to consider, however, the addition of an electrical load, symbolizes a resistor known as RL from B to A. What would happen to the total resistance seen by the source? Think about it. Is RL in parallel with the whole potentiometer or just a portion of it? And if so, which part? What is the relationship of the remaining portion of the potentiometer to this new combination? In this case, it is again extremely helpful to go back to our earlier simplified model of the potentiometer as a series combination of two resistors, RAB and RBC. Using this model, we realize RL is in parallel with the RAB portion of our potentiometer, and the RBC portion of the potentiometer is in series with the RAB in parallel with the RL combination. In the loaded voltage divider, RAB has another path in parallel with it. The parallel combinations of resistors are always less than the smallest resistor in the combination. Therefore, RAB in parallel with RL must be lower than RAB by itself. Since RAB in parallel with RL is in series with RBC, the total resistance seen by the source must go down. Let's see if this is the case. A 1 kilo ohm resistor at 75% means 75% of the resistance is seen between A and B. In this case, it's 750 ohms. The remaining 250 ohms is experienced between B and C. A parallel combination of a 750 and a 4K would be approximately 631.6 ohms. In this case, I could just go ahead and replace this parallel combination with a simplified equivalent of 631.6 ohms. A 631.6 ohm resistor in series with a 250. In this case, our voltage source saw a decrease in the total resistance from the unloaded case of 1 kilo ohm to the loaded case of 881.6 ohms. This is meant to illustrate a powerful fact. No plan survives first contact. This is to say that when undisturbed or not delivering current to an electrical load, a circuit might have one set of characteristics, but another set entirely when it's actually being employed in some fashion or another. An easily observable phenomenon kind of related to this topic is starting an internal combustion engine with the lights on. What happens to the lights while the starter motor is drawing current? They dim because the battery is being asked to provide additional current to the starter. In this case, there's an increased electrical load. We'll go into exactly why this occurs in later lectures about batteries, series circuits, and voltage regulation. The point is, the simple act of placing a demand on a source often changes the nature of the circuit. As a final note about potentiometers, the resistance to position relationship of the B terminal is known as taper. There are two types of common tapers known as linear and logarithmic tapers. We've been using linear tapers for this lecture, where there's kind of a one-to-one relationship between the physical position and the resistance. A discussion of logarithms is a little off topic right now, but for base 10 logarithms, every equal movement of the dial is 10 times the magnitude of the previous position. Where this space represents 1 ohm, this is 10 ohms, 100 ohms, 1,000 ohms, and 10,000 ohms. Logarithmic tapers are sometimes called audio tapers because that's the way our ears respond. Additionally, they're sometimes used as position transducers for things like joysticks. For now, just realize that not all potentiometers are one-to-one, in case you ever run across a logarithmic taper. Honestly, there is not that much to talk about potentiometers other than a general encouragement to get some time in a safe and supportive lab environment and play with these things. Stay organized when you're building circuits using potentiometers. It's super easy to dial one to the exact resistance you need from A to B and then accidentally hook it up B to C and wonder why nothing is working as you'd expect. Once you figure out which terminal is which, clearly identify them using some easily recognizable scheme, and at no time ever let your lab partner use the screwdriver. In conclusion, this lecture took a close look at the three-terminal variable resistor known as a potentiometer. We realized the summation of the terminal resistances from A to B plus that of B to C is always equal to the total resistance from terminal A to C. The proportion of the total resistance seen between any outer terminal and the center terminal is adjustable via the position of a movable center contact. We discussed potentiometers in series, parallel, and series parallel relationships, and briefly introduced the voltage divider in unloaded and loaded scenarios. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.